Welcome to this Llama Research Explainer. Today we're doing something a bit different. We're cutting right through all the hype surrounding autonomous trading to look at the cold, hard, operational topology of private AI. Look, if you're a finance professional or part of a diligence team evaluating these systems, you already know the stakes are incredibly high. So we're going to examine the exact architecture required to build a multi-agent trading system that is secure, auditable, and above all, trustworthy. Let's dive right in.
There's a fundamental truth we've got to internalize right out of the gate. Most autonomous trading failures aren't caused by bad models. They are caused by a missing hierarchy. When an autonomous trading desk blows up, the postmortem almost never points to a single, poorly trained model just making a dumb decision. Instead, it points to a missing chain of command. Somebody or something didn't check a risk gate. A configuration change was pushed during a massive volatility spike. A signal fired, nobody triaged it, and by the time a human actually noticed, the damage was compounding. Basically, it's the absence of strict structure that causes catastrophes.
So, here is our roadmap for today. We'll cover the missing hierarchy, explore the specific roles on an agent desk, detail the handoffs and risk gates, break down vetoes and system halts, and wrap up with a diligence checklist for private AI. Let's get to it.
Section 1, the missing hierarchy, and why structure matters. Let's look at why an explicit, auditable structure is the absolute baseline requirement for any serious trading operation.
Think about a well-run human discretionary desk. They actually get this structure right. The chief investment officer sets the macro thesis, portfolio managers translate that into positions, risk officers monitor the exposure and can pull the plug, and engineers maintain the infrastructure. The problem isn't the human desk structure. The problem is human biology. We are slow, we're inconsistent, and importantly, we're usually asleep between 2 and 6 a.m. We get fatigued, we defer to authority when we really shouldn't, and we might skip a safety checklist on our 400th totally uneventful night when the coffee simply hasn't kicked in yet. Autonomous trading agents don't fix this by just being smarter. They fix it by being relentless about protocol. They execute that exact same separation of concerns, but with machine discipline, 24 hours a day, logging every single decision immutably.
Moving to Section 2, the agent desk, and the triad of control. How do we actually build this relentless protocol? In architectures like Project Cortex, 3 agent roles form the operational backbone. First up is the CIO agent. Just like a human CIO, this agent synthesizes overnight data, stuff like macro signals, earnings surprises, volatility shifts, and produces a morning directive. Think of this as a highly structured, machine-readable, time-stamped daily investment memo. Now, this directive doesn't execute trades, it sets strict boundaries. It dictates exactly which asset classes are in play and where the risk budget sits. It acts as the single source of strategic truth. If the CIO agent says, reduce equity beta, no downstream agent can increase it, literally no matter what a real-time signal says.
Next is the monitor agent. The crucial distinction here is that the monitor agent does not trade. It simply watches, continuously. It tracks broker connectivity, system resource utilization, data feed integrity, and position reconciliation. If anything, and I mean anything, deviates from the baseline, it generates a structured escalation event. It also watches the other agents to ensure they aren't making any unauthorized moves. During those overnight hours, the monitor is your sentinel. It's the only thing standing between a connectivity dropout and an unhedged position sitting there totally exposed until the morning bell.
The third pillar is the engineer agent. This agent handles the actual infrastructure modifications, restarting services, rotating API keys, or deploying updated model weights. But, and this brilliantly illustrates the concept of strict hierarchy, it cannot act on its own initiative. Every single change must be pre-approved. The engineer proposes a change, and the monitor agent must validate that system conditions are stable enough to actually proceed. If the monitor says no, the change queues up. I know it sounds bureaucratic, and honestly, it is. That's exactly the point. The most dangerous failures aren't bad trades. They're infrastructure changes made at the worst possible time.
Section 3. Handoffs and risk gates. Now that we have our triad, let's look at the sequential flow of how they interact.
The flow through a multi-agent system must be deliberately sequential. It starts when signals arrive from your data pipelines. The CIO agent synthesizes these to produce that morning directive we talked about. From there, execution logic interprets that directive into candidate orders, which then run a brutal gauntlet of AI risk gates, position size limits, sector concentration, and drawdown thresholds. Only the orders that survive this gauntlet are routed to the broker. And the absolute crucial point here is this: no step is optional. No agent can skip a gate. If an order fails a gate, it gets rejected, and the system logs the precise reason why. This rigid handoff chain isn't just some workflow, it is literally the system's immune system.
Section 4. Vetoes.
system halts, and the CIT ACE protocol. What happens when that immune system kicks into overdrive?
Let's pose a highly realistic scenario. What happens when agents disagree? Imagine the CIO agent's directive says, add exposure to energy. But the monitor agent detects that the broker gateway is showing elevated latency and partial fills. Both agents are doing their exact jobs based on their data. So who wins?
The monitor vetoes. Full stop. The architecture gives the monitor override authority on execution readiness. The CIO sets the strategy, sure, but the monitor certifies that the infrastructure can safely execute it. If it can't, the system pauses. In a human organization, a senior manager might push a trade through bad latency saying, "Oh, we'll fix the tech later." In a properly governed agent system, the monitor's veto is entirely non-negotiable. The disagreement, the rationale, and the resolution are all written straight to the log.
Beyond a simple veto, there is the CRIT protocol, a command-down escalation that halts all trading activity. This fires under severe conditions: a broker disconnection lasting beyond a threshold, a position reconciliation failure, a drawdown breach, data integrity failures like missing feeds or stale prices, or, obviously, a manual kill switch. When CRIT fires, the system doesn't try to be clever or attempt to autonomously recover. It simply cancels open orders, logs the trigger, alerts a human operator, and waits.
This leads us to one of the most important takeaways from this entire explainer. Refusal to trade is a feature, not a failure mode. Any autonomous trading system that cannot articulate exactly when and why it will refuse to act is simply not designed for real-world operations, period.
Section 5. Diligence for Private AI. Let's wrap up with the enterprise checklist.
If your team is evaluating a multi-agent system, you cannot just accept "we use AI" as a sufficient answer. You have to demand specifics. Your checklist starts with full immutable agent interaction logs. You also need clear decision provenance, meaning you can trace any trade back to its original signal and gate evaluation. Look for evidence from shadow mode testing against live market data. You'll want to thoroughly understand the broker integration architecture, especially around partial fills and rate limits. And you absolutely must know exactly what the system's overnight sentinel behavior looks like at 3 a.m. Finally, demand a clear map of the infrastructure topology and the failover plan.
So the big picture here is this. A multi-agent trading system is really an operational architecture. It's a strict set of roles, permissions, and escalation paths that just happen to execute in financial markets. This is exactly why private AI is so critical for regulated enterprises. Your models run on your infrastructure. Your logs stay in your environment. Your risk gates are configured to your specific risk appetite, not a vendor's default settings. When things go wrong, the audit trail is yours to examine immediately.
At Llama Research, we operate with a very simple conviction. The most trustworthy AI system is the one that can explain exactly when it chose not to act. True intelligence in high-stakes environments isn't just about finding the right action. It's about knowing when restraint is the only mathematically sound option.
I want to leave you with a final, provocative thought to take back to your teams. Look closely at your own operations and ask yourselves, can your current AI architecture explain exactly why it refused to trade at 3 a.m.? If it can't, well, it might be time to rethink your infrastructure. Thanks for joining this explainer. Keep demanding clarity, keep demanding structure, and we'll see you next time.